Okay, so this might be our shortest Nearpod assignment yet. So this is all about temperature conversions. This is in the reference table, okay? Um, and we are going to be focusing on going from one temperature to another and discussing melting, freezing, evaporating, and condensation, okay? So here's an interesting thing. If water freezes at 32 degrees Fahrenheit, what temperature does water melt at? So this is a tricky question. So the idea is that if something is frozen, right? So let's say there's a chunk of ice. That means that chunk of ice, if it's on Earth's surface, is at a temperature below 32 degrees Fahrenheit, all right? So any water on Earth's surface at sea level below 32 degrees Fahrenheit is frozen. And any water above 32 degrees Fahrenheit on Earth's surface is liquid. So the point is that if water is liquid at 33 degrees Fahrenheit, and that temperature drops beneath 32 degrees Fahrenheit, that makes it freeze. Okay, so water freezes at 32 degrees Fahrenheit if we're dropping beneath it. But if we have solid water, which is ice, and it goes above 32 degrees Fahrenheit, that means it melts. So water freezes and melts at 32 degrees Fahrenheit or 0 degrees Celsius. And that's because it's either the temperature is dropping beneath 32 degrees Fahrenheit or it's going above 32 degrees Fahrenheit. The temperature drops beneath, it freezes. The temperature drops above, it melts. So the freezing and melting point is the same exact thing. Now, this up here says water boils. So at 212 degrees Fahrenheit, water is forced to evaporate. And not just evaporate, but boil. Which also means that if you have gaseous water, or water that's already evaporated, and it drops below 212 degrees Fahrenheit, that means some of the water begins to condense, which just means that it becomes a liquid again. So 212 degrees Fahrenheit is the temperature that if it goes or tries to go above that temperature, that means the water is forced to evaporate. If the temperature goes beneath that temperature, that means some water is forced to condense. Okay? Now, technically, that isn't 100% accurate, but that's what we're going to leave it at. Okay? So, we've discussed water boiling, which means evaporating, and water condensing, which means water going in from a gas to a liquid state. We talked about water freezing, going from a liquid to a solid, or water melting, going from a solid to a liquid, or from ice to liquid water like we drink. So, water freezes and melts at the same temperature, and water boils and condenses at the same temperature, just depending on the way that the temperature is going, rising or sinking. Here's room temperature, but let's not worry about that just yet. You will get a question on that. We're going to discuss Fahrenheit, Celsius, and Kelvin. So you can discover this from trying it out, or you can memorize this. It's definitely better to discover it every time. So if we look between 0 Celsius and 10 Celsius, we need to count the amount of little notches up in order to determine the interval. In this case, Celsius goes from 0, 1, 2, 3, 4, and this longish one is 5, and then 6, 7, 8, 9, 10. So each little mark goes by 1 for Celsius, and the same goes for Kelvin. In between 300 and 310 here, we have 301, 302, 303, 304, 305, which is the long one, 306, 307, 308, 309, and 310. Fahrenheit is the only scale that doesn't go by that. So let's do a little guess and check. Let's see if it goes by ones. I just said it doesn't, but let's see. This goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that 10? No, that's 20. So it's got to go by twos. 0, 2, 4, 6, 8. The long one is 10 for Fahrenheit. 12, 14, 16, 18, 20, and then it keeps going up, right? 22, 24, 26, 28, the long one 30 in between 20 and 40, right? And then 32, 34, 36, 38, 40, okay? So If we want to know what the temperature of 160 Fahrenheit is equal to in Celsius, we need to remember that the scales are a little different, right? So here's 160 degrees Celsius, which is one notch above 70. Now, if I forgot that Celsius goes by ones, I need to just remind myself, okay, it goes from 0 to 10, and there's 10 notches there, so it goes by tenths, right? Or by ones. So here's 160 Fahrenheit. So if we want to know what 160 Fahrenheit in Celsius is, that's going to be 71 degrees Celsius. So just so you know, in the United States, and I think in one other country in the world, we're the only ones that use Fahrenheit. Pretty much all the other world, or all the other countries, use Celsius. Now, if you want to discuss Kelvin, all Kelvin tells us, if you remember the energy unit, is that atoms vibrate, and the speed that they vibrate is their temperature. Fast vibrations, high temperature; slow, small vibrations, low temperature. What Kelvin is based off of, if you see, these numbers are really, really high. But if we follow this scale all the way down to 0 Kelvin, which we don't say degrees Kelvin, it's just 0 Kelvin, that means that's the temperature where atoms stop vibrating. They technically have no temperature at 0 Kelvin. Now, this hasn't been done in a lab yet. We haven't got, or science hasn't gotten anything to a temperature of 0 Kelvin, but theoretically it is proven, because an atom or something can't vibrate less than not vibrating, if you follow that, right? So the idea is that if I stand perfectly still, you can't stand more still than still. So an object can't have a temperature less than 0 Kelvin. Now, there are negatives in Celsius and there are negatives in Fahrenheit. We don't like negatives in Fahrenheit. Fahrenheit is very cold. I'm not saying you won't find the answer in the negatives, but humans, it's really cold. Negative Fahrenheit is very, very cold. And the final thing I will say is that Celsius is based off of water. Celsius makes a lot of sense. 0 Celsius is where water freezes and melts, right? So if we drop below 0 Celsius, that's when it snows, or if we go above 0 Celsius, that's when it rains. And then 100 Celsius is the temperature that water boils at. So Celsius makes a lot of sense, and Fahrenheit, not so much, okay? So that's the general idea. Hopefully this makes sense, and you'll get some practice problems with it.